Hi everyone, I'm Daniele Reda, and today I'll speak about understanding how environmental design matters for DeepRL. In this work, we'll take a look at DeepRL for character locomotion from a different perspective, and that is the one of environmental design. Let's start by stating the obvious. RL has been a popular and common technique for physics-based character animation, but it can be brittle to use RL algorithms for this kind of tasks. On the other hand, in the RL community, there has been significant effort into improving RL algorithms. But in most of these cases, the environment has always been assumed as given, as a black box to interact with. This has obscured the importance of RL environment design. In fact, we claim that there is an attribution bias. In fact, the RL component is just one piece of making this kind of locomotion tasks work with RL. And more often than not, we are too quick to attributing all of the credit to the RL component, as if the environment didn't play any significant role at all. Instead, both the algorithm and the environment play an important role, and understanding how one works with respect to the other is very important. What we are trying to do today, what we are trying to answer in this work is which kind of aspects matter when we are designing an environment for RL, more specifically for character locomotion. And to answer this question, we have to look at the usual RL loop, in which there is an RL algorithm and an environment. They interact with each other. The RL algorithm sends actions to the character transitions its states, and then sends back the new state and a reward and a terminal signal. So when we try to answer which aspects matter for RL environment design, we can further divide this question by trying to understand what are the reward and terminal signal, what should they include, and how should they be used. For the state, we can ask ourselves, what is the best state representation for representing the character so that the RL policy can take the best possible action? For the action space, we can think, what is the action space that we should use? Should we output torques? Should we output desired joint angles, or what? Also, the initial state distribution plays an important role. And in the same way, the delta t, the control frequency of the RL policy, can also affect the final results. For time constraints, we will not go through all of the analysis that we did in the paper, but we invite you to read the full work. Instead, here we'll just take a look at a few interesting results that we think that are very interesting. Let's first start by describing the experimental setup. For algorithm, we use the TD3. It's a widely used off-policy model-free algorithm. And for simulator, we use PyBullet. We decided to use TD3 because it usually gets very good results for locomotion tasks that are the one that we are using with the PyBullet simulator. And more specifically, we are using the default characters, half cheetah, ant, hopper, walker, and humanoid, that are widely used for this kind of benchmarks. For each of these environments, the task is locomotion, and you get a higher reward by walking forward as fast as possible. As I said, let's first start with initial state distribution. What is this distribution? Well, the initial state distribution is that distribution of states from which you sample the starting state. The starting state is the state in which the agent is placed into the environment, from which to start rolling out the trajectory, and so exploring and collecting data. By default, this initial state distribution is very narrow, almost deterministic, like in the plot on the left, in which the square represents the state space and all of the trajectories start from more or less the same state. what happens when we change this initial state distribution so that we make it larger and so that the trajectories don't always start from the same space, and basically the RL agent is always placed in a different position in the state space? Well, the results are very interesting. If the initial state distribution is very narrow, we will have a much faster learning because the tasks will be easier, since the RL agent is always placed in a state that has already seen, and so it already knows how to map to a good action. As we increase the initial state distribution, we'll have harder tasks and it will take longer to learn. But in the end, the final policy will be more robust and will have better generalization to a wider range of states. Although there is a problem. If the initial state distribution is too wide, then the RL agent is placed into the state space all the time in a different place. And so it is unable to create a mapping from states to actions, and so it is unable to learn at all. Regarding state representation, we can ask ourselves, what should we include in the state representation? What are the best pieces to add in the representation to help the policy get and learn faster the best possible actions? For example, we can ask ourselves, what about adding Cartesian joint positions that are widely used in the graphics and animation community? That is, adding the Cartesian distance between the root link and the different joints of a character. It turns out that it helps only for some environment. For example, for humanoid, it gets faster learning, but the final policy doesn't change much. Another representation that we could add is a contact variable. This contact information is a binary value that tells if that specific joint is in contact or not with the flora. It turns out that adding a contact information helps sometimes. For example, for ant, which has multiple points of contacts. In fact, it has 8 legs. Instead, for walker or for humanoid, it doesn't make any difference because we think it's because it just has 2 points of contact, so it doesn't make much of a difference. Another interesting experiment that we did was the one with pre-trained representations. So we learn a representation and then we use that one as a new representation for learning a policy. What we did was training a standard RL algorithm so that the policy receives states as input and outputs actions. And then after this policy has been trained, we remove the final layer and we use the output of the final hidden layer, everything up until that point, as a representation encoder, so that the default state gets as input and the output of that hidden layer is used as the new learned representation for training a new policy. We expected that this would work really well, since that representation was learned specifically for taking actions. Although, surprisingly, it's not helping. Actually, it often fails to learn at all, and when it learns, the policy is suboptimal. Speaking about actions, we can ask ourselves many questions. For example, what should be the control frequency, and how does it affect learning? The control frequency is the frequency at which the policy interacts with the environment. And we can tweak this one by changing the action repeat value, which is a very usual, it's a widely used hyperparameter in RL tasks. The action repeat value simply represents the number of times that the same action is used to step the environment before giving back control to the RL agent. And it turns out that this action repeat value has a significant impact. In fact, by increasing the action repeat value, and so lowering the frequency of the policy, results in having bad policies for working. Still, for actions, the choice of action space can be very important. outputting desired joint angles instead of the default output that is torque for each joint angle. So outputting the desired joint angle and using then a PD controller to translating this desired joint angle into torques is something that is proven to be really good for imitation tasks. For RL tasks, instead, PD controllers can improve the learning speed, but the final performance usually suffers and it is suboptimal with respect to the original default policy output that is outputting the torque for each joint. Speaking about the reward, we took a look at the survival bonus, which is one of the different components of the reward signal. And this survival bonus is the constant reward term that is awarded to the character just for staying alive. And this simple term has a big effect on the final policy. In fact, if the survival bonus is too small, the policy fails immediately and the character falls all the time because it is not motivated and it is not incentivized to learn. Instead, if the survival bonus is too big, the character becomes too timid to walk because it gets already a good reward and it just doesn't want to learn any further. We have a further analysis in the full paper, but the take-home message is that the environment design indeed matters for RL, and often it matters even more than the choice of the algorithm itself. We thank you for your attention, and we welcome your questions both here and in the chat. Thank you.